So we have started discussion on certain approximate method using which we can get reasonably accurate values of the natural frequency of a system, elastic body system, where analytical formulation will not be possible. So there are two approaches. One is in such cases where the geometry is not simple enough, amening the problem to or making the problem suitable for analytical solution, as in case of uniform beam, bar, uniform shafts. Or that means two methods will be either use computer or use some quick approximate method to get some idea about the natural frequency. For design purpose, sometimes this approximate method may be considered enough rather than going for a complete computer solution. So we have already demonstrated that we use the Rayleigh's principle. Rayleigh's principle says that for an undamped system, in the steady state, the maximum kinetic energy during free vibration must be equal to the maximum potential energy, which in case of elastic bodies is predominantly the strain energy involved. So using this principle, what we found in case of bars, that this is equal to that means the total kinetic energy of the whole elastic body in its peak value in the normal mode oscillation can be expressed like this, where Xa is the assumed deformation shape or mode shape, whereas this will be in case of longitudinal oscillation. And we have seen by applying this method to a longitudinal vibration of a cantilever bar or one end fixed bar, that our result was reasonably accurate, even though we assumed the mode shape which was not satisfying all the conditions. But one thing we should keep in mind, to get meaningful values, that whatever mode shape we assume, they must satisfy the geometric boundary conditions. Geometric boundary conditions are those which depend on only the deflection or the slope of the particular cross section, whereas the other kind of boundary conditions, like they are, for example, this end is free from, say, a force, whereas this end is free from any displacement. So this is a geometric boundary condition, but this end is free to move, but its force is 0. That's a non-geometric or dynamic boundary condition. So at least the geometric boundary condition should be satisfied, and so we took something like this. Very simple form, and we reasonably got the answer. So now I think let us go to the other type of vibration problem, which is more common, that is transverse vibration. Now, in case of transverse vibration, the kinetic energy expression at the peak value will be same. That means an element we take and the element mass is given by its volume, that is A into dx, that is the length of the element. If we take and we take one element of length dx, so in bend condition it comes here, it gets subjected to bending moment, which is m, and here it is m plus a small change dm, we do not bother much. The force is here, say for example V, and here again it is G plus V, resultant force is also very small, and the displacement of this from here to here is given by u, which is a function of x and t, but which we write as this as a function of x and this is cosine omega t. We assume this normal mode oscillation to derive at the Rayleigh's quotient. Now, in this case, the velocity will be, maximum velocity will be same as omega xa, and so the square of that will be, mass will be a dx into rho, then half into velocity square for the whole member. So that will remain same as we had in this case. But however, how much is the maximum strain energy, that we have to derive, and let us find out this element. Now, we all know that if the element is like this, its length is dx. Its flexural rigidity at this particular location, it will vary along this path, but flexural rigidity is say E I. That means E is the modulus of elasticity of the material and I is the second moment of area. Now, this is subjected to a bending moment. We know that in such case the energy in this member will be half m into, now the whole thing we know is going to be in the form of bending. So, if we fix one end, then the other end is going to rotate by an amount d theta. If we consider, if we try to match it with this and try to rotate the other end, the total amount of angular rotation of the end where we are applying the moment is d theta. So, therefore, it will be half m d theta. We know that because it is a gradually applied moment, and so the total work done by this moment will be half into m into d theta. Because moment also slowly increases from 0 to maximum value when the deformation or the rotation of the end is already d theta. Now, if this is dx and if the distance of the neutral axis is r, that is r is nothing but the radius of curvature. We know from bending theory m by I is equal to E by r. And from geometry you also know that if this is dx and this is r, then the relationship between the three quantities are given like this. So therefore, du max, that means maximum strain energy stored in this element, is given by half into, now here d theta, we can write this now using this as dx by r. Now r is nothing but ei by m, so it becomes half m square by ei into dx. So this has to be now integrated for the whole member starting x is equal to 0 to L. Now how much is m? M we already have found out. Let us first write this. Now we have already shown earlier that m is nothing but ei by and with the sign convention which we use for positive moment here, and when the neutral axis bends in such a way that with x its slope gradually decreases, so then minus sign comes, minus, and 1 by r we have already derived as so. Once we have integrated, then this becomes, this is u max. So this, using this, now putting the same here, we get half E I into thus the Rayleigh's, when we equate the two, the natural frequency square we get as so it is slightly different. In this case, we are having half ei into d2x a dx whole square into dx, and the expression for the natural frequency we get like this. So this is for transverse vibration, and let us see what kind of results we can get from this. We will take up an example. First, let us, for the sake of comparison, we will take up that type of example for which we know the exact solution. Let us take this example. It is simply supported. the coordinate system we fix like this as before. The total length L and its modulus of elasticity is EI, cross sectional area is A and density is rho. And it happens to be so that in this particular case of simply supported uniform beam, EI, A and rho, they are all constant. So now, what are the boundary conditions? Because the assumed mode shape XA of the deformation pattern has to satisfy as many boundary conditions as possible and at least the geometric boundary conditions. So boundary conditions are like this. At x is equal to 0. Now we know that at this end, what we know is deformation or displacement is 0. Similarly, at x equal to L, again at the other end, displacement is 0. These are the boundary conditions of geometric nature. Now the other boundary conditions which comes that here again there is no moment acting. That means if moment is not here, that means the second derivative dxa, which is proportional to the moment, should be also 0. And since it is simply supported at both ends, so these are the 4 boundary conditions. So now we have to assume mode shape. Say, let us take a case 1. X A is simply if we assume like this, the first boundary condition, that is at x is equal to 0, capital Xa is 0, that is true. Similarly, at x is equal to L, Xa is 0, which is again true. So the geometric conditions are satisfied. Let us see how much is d2 Xa dx square. That is equal to minus. If we differentiate this twice with respect to Xa, we get this. So which is not equal to 0. Neither at x equal to 0 nor at x is equal to L. So these 2 boundary conditions are not being satisfied. So therefore, now once we have assumed Xa and we have found out the expressions for x2 prime A, only thing we have to do is to substitute Xa in this expression and get the value of omega square. So to do that, so what we find that Ei is constant, but in reality, if it is not constant and it's a function of x, we can keep it inside that. this is equal to EI into, now d2x a dx square is minus 2c by L. If we make it square, so we get, so what remains inside simply 0 to L dx, which is nothing but simply L. That is 4 c square EI by, that is the numerator. The denominator is rho A is again constant because it is a uniform beam. What remains inside this and if we do this integration, we will get hence equating the two, or rather finding out the omega square like this, omega square will be 4 c square EI L into, sorry, 30 or omega is approximately equal to so this is the value we obtained from this assumed mode shape XA, which satisfies only the geometric boundary condition. We should remember our exact value of omega answer. What we found out from our mathematical analysis was actually it was pi to the power 2 pi square. So it is 9.86. This is actually pi square. That is the exact value. So you see that it is reasonably accurate. 9.86 and 8.95 is approximately 0.1 difference in 10. That means just in 10 it is 0.1, so it is just 1% error. In spite of the fact we made a very approximate assumption. If we now, for example, if we try to improve upon that, suppose let us take up an expression for XA which satisfies all the 4 conditions, and let us see what happens. एक पेन भी ले आए काला काला पेन वहाँ पर जो है वो ठीक। If we take another choice, say XA is if we make this choice, then XA is that, and d2XA dx square is this. So now you see that if we put x equal to 0, XA is 0, and if we put x is equal to 0, d2XA dx square is also 0. So it satisfies both the conditions at x equal to 0. Next, if we put x is equal to L, so it is L4, this is L4, so 2L4, minus 2 L into L cube, so minus 2 L4. So x is a 0 at x is equal to L. This is satisfied. Next, if we put x is equal to L here, this is minus 12 L square, this is plus 12 L square. So d2XA dx square is also 0 at x is equal to L. Thus, all four boundary conditions are satisfied. Now, still it is not a very complicated expression, but obviously integration etc. will be little bit involved, and let us see what we get. If we substitute XA and X double prime A in the expression and find out this numerator and denominator, we get Now let us compare the result with the exact value what we received from analytical method done in the previous module. So if we compare this with the exact, which is this, you find up to second decimal place there is no difference. The difference will be found only in the third decimal place, and that too again having this. So when you satisfy all the boundary conditions, the result what we normally receive is very accurate, except for some special situation. One thing of course we should remember, we have not calculated up to the third decimal place. If we do it, we will find still this will be slightly higher than the first natural mode we find by exact method. So therefore what we get from this is that whatever value we get by the method of Rayleigh's approach, we have shown it earlier also, is always slightly higher than the exact value. So as a result, what is happening, this Rayleigh's method will give us that will give a limit. Whatever value we get, the actual value of the first natural frequency will have to be below this. And by Dunkerley's method, if we get something, the value of omega 1 like this, then you know the actual value of omega 1 will have to be above this. Thus, we get a band, and the exact omega 1 must lie in this band. So therefore, if we can make by some method this band as narrow as possible, then omega 1 can be estimated in a very accurate way. Now the question is that in all these cases we could solve the problem exactly. So what we have gained by this? We only got an approximate answer. That will be apparent if we take another example. This example is that let us take a tapered cantilever beam the length of the beam is x, length of the beam is L as before, and the depth, that means in reality this beam is cantilever beam with constant width. So the width is constant and the thickness is uniformly varying, and at the other end it becomes h, and at this end it is 0. So that means the width is uniformly increasing and it becomes h. The depth is increasing and it becomes h here. The width remains constant. So the material property remains constant, which is rho, that is the density, and E, that is the modulus of elasticity. So with this, one thing we have to, so what are the boundary conditions? Now this is an example to indicate that in reality boundary conditions are not on Xa or these things. Boundary conditions are deflection, slope, shear force and moment. These are the real conditions, but they get translated into conditions on Xa. So here we will find sometimes it may be important to note the condition on the actual condition. That means at x equal to 0, moment is 0, bending moment is 0 because it is a free end, shear force is 0. At x is equal to L, that is the fixed end, deflection is 0 because it is a fixed end, and slope is 0. So we now choose a mode, we assume a mode shape Xa in such a way that all the boundary conditions are satisfied. We will do it here like this. If Xa is this, then Xa prime, that is dxa dx, will be equal to and d2xa dx a square is now let us see the conditions which are being satisfied. At x is equal to 0, at x is equal to 0, is the moment 0? Now, if you try to see whether this is 0 or not, that is not the condition here. Here, the cross-sectional area is 0. Since cross-sectional area is 0 because it is coming to a point or a thin edge, so whatever may be the value of this, moment applied will be not just this, but you have to take care of EI. So that EI is 0 because I is 0 at this end. So therefore, bending moment at this end is 0, though the second derivative is not 0. So this is a very important point to observe. Secondly, shear force. Shear force will be then whatever you will find shear force will be given by the third derivative, which is 0 here. Of course, even otherwise it would have been 0 because the area is 0. So both the boundary conditions at this end are being satisfied. Let us go to x is equal to L. X is equal to L, x is equal to L, what happened? Deflection is 0. So we find from this expression that deflection is 0. Similarly, the slope dxa dx is also 0 at x is equal to L. So therefore, all four boundary conditions are being satisfied. So this is a very special case to keep in mind, that we need not all the time be carried away by the expression of this and trying to see. It also depends on the cross-sectional area, and this is a case where we find that without satisfying all the conditions on xa, because I being and a being 0 here, we satisfy those boundary conditions. So four boundary conditions are being satisfied. Now let us apply this to the expression for. Before we do that, so the two quantities A is a function of x, which is B, that is the width, into the depth. Depth will be x into h by L. That means if we go here at x this will be linearly. At x is equal to L, depth is h. So at x is equal to x, this will be h by L into x. And if the width is B, then we just multiply by B. So this is the cross-sectional area. Similarly, the second moment of area, that is I, will be xh by L cube. E is constant. So if we substitute this in the expression for omega, we will get omega equal to so this is the answer we obtain with that function as the assumed mode shape. Now this is a particular case where it is possible, though it is a non-uniform cross section being linear, we can solve the problem exactly by analytical method, and exact value of omega 1 is found out to be thus we find that the result we get by a reasonably simple mode shape assumption is quite accurate and the error is very low. But all the time we notice that the frequency which we get by assuming a mode shape which is not the exact one will be always higher than the exact value. So this I think the more problems can be solved, but that is predominantly an algebraic manipulation most of the time and solving integrals. So there we will not go further in that direction. Rather, what we will try to see that is there are methods by which we can improve the accuracy. That should be our concern. And the one very important, or rather I will say very convenient way of improving accuracy of the method following Rayleigh's approach is to use Graml's modification. So what we can do quickly now we have seen that omega square we are expressing, which is the Rayleigh's quotient as 0 to L here. With little bit of thinking, it can be found out that the errors are getting introduced because of this double differentiation. One is, of course, that XA itself is not the exact mode shape which is valid. It is slightly deviant or slightly different from that. That is a source of error. Plus, whatever may be that, this double differentiation is a source of error in the whole process. So what Graml did, he tried to formulate the same thing, that means equating the maximum kinetic energy or maximum potential energy during the normal mode oscillation, but formulate it in such a way that this double derivative is not necessary. So what was done is that he considered that the system or the beam or flexural member is subjected to a peak inertial loading. That means during every cycle there is one period when it goes to the extreme, it is subjected to inertia forces. Say for example, if we take, say for example, any kind of beam, but we will take an example like a cantilever. So what will be the inertia force acting? Inertia force acting on any particular element will be the mass of the element into acceleration of the element at that peak point, that is peak acceleration minus. So it can be either in that direction or in this direction. So it will be something like this, inertial loading. And this inertial loading can be written as omega square, and the element here will be the d mass dm into so it will be a distributed one. This is the inertial loading. And what we will do, we will consider that this is the loading on the whole thing. Now, if this is the loading on the flexural member, we can find out the bending moment due to this. As a function of x due to it is a distributed load, and let m be the bending moment due to that. Now, we have already seen that du of an element is half m into d theta, which was equal to half m into dx by r, where r is the radius of curvature at that bent condition at one extreme end. Now, from beam theory, or other simple expression, that m by I is equal to E by R. So, if we treat this element as a beam, the length of the beam is dx, radius of curvature due to bending is r. Then we have seen just now, little while ago, that r is, or rather we can replace r as d theta by dx by d theta, or simply you can write this as r d theta is dx, r is equal to we will come to that later when we here replace. So, using this now, we get for the element maximum strain energy stored is half. Here R is equal to m by EI. So, now let us use this here. It will be an m square by EI 1 by r, m square by EI So, now from this we will get maximum potential energy, the whole will be half and T max of course remains as it is. So the procedure is now that if this be the inertial loading, which is in terms of omega and xa square, let us find out the bending moment in terms of xa square omega, no differentiation involved, and then substitute it here and integrate. And then when we equate Umax and Tmax, this will yield the value of omega an equation which will be better in accuracy. The reason is this, that we are avoiding this double differentiation of xa, which has been assumed. So any assumption, we know that in any kind of assumption of a curve, the slope, the order of error in that will be more than the order of error in the actual function. And that is why we are now getting a better result as we are doing the whole calculation without differentiating xa.